Thank you, Fred, and thank you to our host. And it's really a pleasure to be here. I've had the chance to meet and talk with people. Sounds a little bit loud now. Talk with people today, and looking forward to another day on campus tomorrow. So I'm going to start by. Doesn't that seem loud?
Yeah.
Yeah. Okay. Oh. Testing, 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 testing. It's rare for a dark matter searcher to have too much signal. So I'm going to be telling you a story about gravity and if Newton and Einstein got gravity right, why we think there's a big piece of the story missing, and how we're using this one candidate, the WIMP that Fred mentioned, to see if that's the dark matter, to see if nature has produced a particle that we can actually go and detect in the laboratory. So I'll start by sort of introducing how we think about gravity in this context, and we'll zoom out and look at larger and larger structures, and then talk a little bit about the hypothesis of this WIMP. How do we think this WIMP was produced in the Big Bang, and why it hangs around today in the dark matter as the dark matter of the galaxy, and therefore what sort of experimental challenge that presents to us. Once you define a signal, then you have to deal with the backgrounds. What are the things that could get in the way? And so, of course, that's a lot of what we sweat on a day-to-day basis. And so then I'll talk to you about some of the technical challenges, and then where we are in the series of experiments that we're running, the LUX and the LUX-ZEPLIN experiments. So the first theme is that the universe is mathematical. There aren't actually any equations in the talk, but the universe is mathematical. Isaac Newton, who developed calculus while home from avoiding the plague during college, came up with a mathematical description of gravity. He taught us how to think about objects that were thrown and falling on the Earth, could also be put into orbit, and of course, together with the data and observations from Kepler and others, gave us an understanding of universal gravitation. Gravity also explains what happens if you're in South Dakota, where we're doing our experiment, and you wanted to flip a snowmobile. Here's a nice gravitational parabola. That is not me in the photo. So let's start with something very familiar, the solar system. A way that we can weigh the sun is by attributing it as the gravitational source that keeps all of the planets moving in their orbits. And we can make a plot of the orbital speed of each of the planets versus their distance from the sun. And to every freshman physics student, this makes complete sense. Mercury is close, the gravity is strong, and there's a very, very strong centripetal force, so the orbital speed can be very fast. As you get further and further out, the strength of gravity, the famous inverse square law, is getting weaker and weaker. You have a weaker centripetal force, and so now a circular orbit with that weaker gravity is moving much more slowly. And so that's how we can make a nice, complete, coherent picture of the solar system. We can apply these same ideas to an entire galaxy, looking at the stars, and not in this picture, but the gas. And astronomers, I'm actually a particle physicist, astronomers know how to study this sort of image in great detail and look at the Doppler shift of the various objects that are moving, so like the equivalent of a train pitch changing. The colors of the light will shift whether stars are moving towards or away from the observer, and they can piece together what the velocity profile of a galaxy looks like. And when you make a similar sort of graph, again, the rotation speed versus how far out your test particle is, whether it's a star or gas that's emitting light, and you make a graph of those speeds, and you compare that to if you just added up the gravity from all of the visible stuff, all of the luminous stuff, and you compare those two things. And if stars and gas, the visible stuff, were the whole picture, then just like the picture of the solar system, you'd expect the speed to fall off. As you got further and further away, the centripetal force and the gravity would be getting weaker. But in fact, what's observed in virtually every galaxy that's been studied is that out to very large distances, things are moving very, very fast. So either, why isn't the galaxy falling apart? Either we don't understand the force of gravity on these scales, or there's a missing component. There's additional stuff different from the stars and gas that are providing the gravitational forces to keep things in these very, very fast orbits. And this work was actually pioneered in the 1970s by Vera Rubin, one of the real stars of the whole dark matter story, and she passed away just less than a year ago. So now we can zoom further out. So now now there are bound structures called clusters of galaxies. So each of the yellow blobs in this Hubble photograph itself is a galaxy, and those galaxies are moving around each other under the force of their own mutual gravity. They're sort of holding themselves together. And one of the ways of estimating the total mass of weighing this cluster is by taking advantage of a phenomenon called gravitational lensing. So we learned from Einstein that mass bends the space-time around it. So if you have a fortuitous alignment of a telescope, some very bright background object, and some very massive cluster in between along the line of sight, then this background object can get split into multiple copies. And by measuring the amount of lensing, you can work backwards to figure out how much mass was present. What is the total bending of space-time? And then you compare that to the luminous stuff. And again, as the theme of the talk would suggest, you find that there's a lot of matter that isn't accounted for by the luminous stuff. And so you can do a mathematical fit to figure out, given the strength of the lens, how much matter is present. And so the spikes in this projection show the density associated with the visible objects. But then to get the strength of the lens right, you have to impose that there's a smooth hump of additional mass spread out through the cluster. So that's how we weigh the cluster. Now, Fritz Zwicky, who sort of started the field of dark matter in the 1930s, you can see he's kind of a bit of a character. He was a contemporary of Edwin Hubble. He was studying the Virgo and Coma clusters, not using gravitational lensing, but using a theorem called the virial theorem, where he compared the mean kinetic energy and the mean potential energy to figure out how strong the gravity in these clusters were, and that was kind of the beginning of the field. So now we can step even further out and use cosmology to weigh the entire universe. So I'm going to take a few minutes to go through this slide. It's pretty detailed, so please bear with me. When you start talking about how the universe behaves on cosmological scales, the two main ingredients are the energy and the matter, and they behave in different ways. Energy tends to be a sort of an anti-gravity or repulsive force. You may have heard of the dark energy, which is one of the big mysteries in physics today. And then the other piece is the matter, which is the stuff that does the sort of attractive gravity that we're used to. And these two things sort of work a little bit in opposition. By using a set of different cosmological observables, we now have arrived at what we call the standard cosmology, which means we think we know how much energy and how much matter there is in the universe. So one of the ways in which this became apparent is by using supernovae, a certain class of supernovae, as standard candles. So by knowing what their intrinsic brightness is and measuring their apparent brightness as a function of distance, we could kind of work out the time history of the universe. And what that tells us about is it constrains sort of the difference between these two quantities to the extent that the dark energy is repulsive and the dark matter is attractive. The tug of war between those two forces, if you will, kind of determine the expansion history of the universe. And using the apparent brightness of the supernova, you can constrain the difference of those two quantities. So that gives us a constraint of the matter density and the energy density lying somewhere inside this oval. Okay. Next, we turn to the 3-degree cosmic microwave background radiation. This is actually an older result. This is not even the best data now available. That's from the Planck instrument. And because we understand, so this is the radiation that was emitted when the universe was just a few hundred thousand years old. And by studying the pattern of that radiation and understanding the underlying microphysics, we can extract from this picture sort of a standard ruler. What is the physical distance scale of the early universe? And we can now measure its apparent size in the same way that we measure the brightness of a standard candle. We can now measure the size of a standard ruler, and that tells us about the overall geometry in the universe. And it turns out that it's the sum of the energy density and the matter density which tell us about the overall geometry. And so this orange band here is the constraint from the cosmic microwave background. It's sort of equivalent to the sum of those two terms. If you increase the matter density, then you should decrease the energy density so that the sum is fixed. And it's the CMB which tells us about that sum. So far, so good. We have these two constraints intersecting at now a smaller oval. And then the third piece of the puzzle is what is the ordinary matter doing? So in the early universe, the ordinary matter was interacting with the photons. And so by studying the CMB, we know how that matter was distributed in the early universe. And of course, we can make observations of how that matter is distributed today in stars and galaxies. And by tying that picture together, we can make a constraint that tells us about the overall matter density. And that's this orange band. Now, these three things didn't have to necessarily intersect. They could have been three different points of intersection, which would have suggested, well, we don't really quite understand what's going on yet. But then there's been this very nice concordance where we now have this very tight ellipse to satisfy all of this data that tell us that the energy density in the universe is about 0.7, and the matter density is about 0.3. And this is in sort of the units of cosmology called critical density. Okay, what do we know about the ordinary matter in the universe? We get some information from the cosmic microwave background. The ordinary matter in the universe was interacting with the photons, and so there's a lot of information encoded here. But we also know something about how the elements in the early universe were synthesized, how much hydrogen and helium and the other light elements. There are very tight constraints on the amount of ordinary matter, and this was first studied by looking at clouds of hydrogen and how much deuterium was in them. And that told us that the total amount of ordinary matter was only about 5%, or 0.05 in units of critical density. And these measurements were further tightened by what we learned from the cosmic microwave background. So the puzzle that we're left with is that the total matter density in the universe, the x-axis, if you will, on this graph, lives quite far away from the value where ordinary stuff is. And so what we're trying to figure out is what is this discrepancy? What makes up the dark matter? We now know what it isn't. We know that it's not the stuff in the periodic table. We know it's not protons and neutrons and elements and all that. So what might it be? So we have to come up with new ideas for that. And one leading hypothesis that we've actually been chasing down for over 20 years is the so-called WIMP hypothesis. The idea that there's a weakly interacting massive particle. So massive, it has gravity. Weakly interacting because otherwise we would have seen it already. And we apply the idea that we also learned from Einstein that you can convert energy into mass. And that in the early universe, we basically had a particle factory. In the hot, dense plasma of the Big Bang, we had so-called standard model particles, quarks and antiquarks. These are the stuff that protons and neutrons are made of, colliding at very high speed, very high energy. And if a new type of particle existed, then it could be produced in those collisions. So the hypothesis is that if this particle exists in nature, it could be produced in the Big Bang. The question is it still there? And so now I need to introduce a concept that we have in particle physics that we call the cross-section, which tells us about how frequently different objects will interact with each other. So picture, if you will, you're playing billiards and a friend decides to blindfold you, and he sets you up with the cue stick, and you try to whack the cue ball. With 3-inch billiard balls on a 1x2 meter table, there's a reasonable chance that you'll get some collisions, right? The particles are close enough together, given their physical size, that some collisions are going to take place. But if you shrink down the billiard balls to, let's say, a few millimeters apart, and the billiard table is the same size and there's still 15 balls, now there's a much smaller chance that an interaction is going to take place. So the cross-section of the particles or the balls that are interacting is going to determine the probability with which they interact. Okay. So now, if a WIMP and an anti-WIMP encounter each other in the early universe, then they could annihilate back into standard model particles. This diagram here, so-called Feynman diagram, can also run in reverse. So WIMP and anti-WIMP can go back into standard model particles. So it's not helpful to us as dark matter hunters if our candidate was produced but then immediately annihilated away. On the other hand, if you shrink the cross-section of the WIMPs, now they're further and further apart. If you shrink the cross-section, then a WIMP and an anti-WIMP are much less likely to find each other. And so this is why we are pursuing candidates that have very weak interactions. By weak interaction, we mean exceedingly small cross-section. So the hot plasma of the Big Bang produces these WIMPs. They have very small cross-sections. Then they'll fail to find each other to annihilate. What further helps us is that the universe itself is undergoing rapid expansion, the Hubble expansion. And so the WIMPs were also further and further apart on average. So this was like take your 3-inch billiard balls, but now set yourself up on a billiards table the size of a football field. Again, because now the balls are so far apart on that spatial scale, they're not going to find each other to annihilate. So putting together this idea of cross-section and annihilation rate and how much dark matter we're looking for, this 0.3 in units of critical density, we can start to constrain what the properties of the WIMPs are going to need to be if they're going to solve this dark matter problem. And that also leads us to think about how we might go and detect them. Right? So if you go back to slide 3, that was the rotation curve showing us that in galaxies there's a lot of dark matter. There's something floating around that's providing all of this gravitation. So if the source of that missing mass is a WIMP, and we know about the local gravity, and we have said something about the properties of the WIMP from these early universe arguments, that they have some interaction rate, that they have a certain mass range, and so forth, then we can begin to design an experiment, a terrestrial experiment, in which we're moving through this dark halo of the galaxy, and see what can we say about the WIMPs. So the funny thing about a WIMP, so if you know about neutrinos, these are similar to like very heavy neutrinos. They interact so weakly that if you had a lead brick that was a light year in length, and you sent a WIMP or a neutrino through it, it might scatter once or 0 times. In other words, ordinary matter is virtually invisible to this stuff. The reason being that these particles don't have electric charge, right? The only reason my feet don't sink through the floor is that the electrical charges in my feet are repelled by the electrical charges in the floor. Take out the electric charges, and then you only have maybe weak interactions to work with. And so these particles are very penetrating. Okay. So now what saves us? What allows us to maybe, we don't have detectors that are light years across. That would be absurd. What we do have, though, is about 10 to the 16 WIMPs per year going through a meter scale detector. And a meter, as it about 10 to the minus 16 light years. So I just put in some numbers here to suggest that things are starting to be tractable, even though a given WIMP would travel through light years of material without interacting. If you've got 10 to the 16 per year, enough WIMPs to make up this missing gravity, and you have a detector that's about a meter across with that much material, then you have a hope of seeing maybe a few events per year in a macroscopic tank of material. So that defines our signal. A large detector sensitive to individual recoil events, a WIMP striking a nucleus in the detector. Okay, so that's the signal. What about background? So the whole idea of background is kind of what we live with on a daily basis. So just to illustrate this, right? When you do astronomy, you do astronomy at night, right? Because during the day, there's an enormous background, the scattered sunlight, right? The stars are still there during the day. In fact, we got to see some in Oregon a few weeks ago. Somebody turned the sun off during the day, and we got to see a few objects during the day. So that verified for me that, yes, this argument is actually correct. The stars are not turned off during the day. Okay. So in the context of a dark matter experiment, the main backgrounds that we face are due to radioactivity and other sources of particles. So you're looking for a few interactions in a macroscopic tank of material per year, but there's sort of radioactivity all around us. Our own bodies would be too radioactive to stand next to a dark matter experiment when it's operating. So now I want to sort of segue into what our detector technologies look like. This was actually an early dark matter search in the late 80s. It was just a single chunk of germanium, so a semiconductor material cooled down to 77 degrees, where if a particle interacted, it would create some ionization, some electric charge that you could then drift through the detector. And you could measure how much charge came out on an event-by-event basis and make a graph of the energy that was transferred to the detector versus the event rate. And what you see is a bunch of peaks associated with known sources of radioactivity. So if nature had chosen a WIMP that was, let's say, a heavy neutrino, it would have produced a spectrum in the detector sort of roughly where this red line is. Right? Now, obviously, that signal didn't show up in the detector. You saw that you were limited only down here by radioactivity, and so you could say, well, a WIMP with the parameters that would give rise to this particular recoil spectrum can be ruled out by these data. Okay, but what if the WIMP had a lower cross section? Then maybe the recoil spectrum would have just been hiding in the background. Okay, so if you dial down the cross section, then for this WIMP, we can't say anything. Okay, so by pushing down the radioactivity, we'd be able to make more progress. Another thing that we don't know about the WIMP, in addition to its cross-section, we don't know its mass. We know roughly sort of an appropriate mass range, anywhere from a few times the mass of a proton to a few thousand times the mass of a proton. So since the theory doesn't tell us the mass of the WIMP, what we have to do is say, well, there's not just a single recoil energy spectrum that we have to consider, but what if the WIMP were lighter? Well, then there would be more of them, but they wouldn't collide with your detector with as much energy. Or if they were heavier, then they would deposit more energy, but at a lower rate. And so what we do is we run recoil spectra for a whole series of different WIMP masses, and we ask for each of those, did they show up in the data or can they be excluded? And we put all those points together, and I'm going to show you a few more graphs like this. So we run an experiment, and let's say we don't see anything. Then as a function of the WIMP mass, we say, well, if the WIMP mass were at this green dot, it didn't show up with a particular cross-section. It was hiding in the data or doesn't exist. So below this point, we can't say anything. Above this point, we can say nature didn't produce a WIMP at that strength. And we piece together all these points, and we make this curve, and we can say if nature had chosen a WIMP with a cross-section or a mass above this curve, then it should have shown up in our experiment. So this is a way of charting our progress, of how do you quantify that you didn't see something. And obviously you want to show your funding agency that you're making progress, and so you have to, even if you don't see anything, you have to push this curve down the page. And also, your competitors' curves are there, and I'll show you a little bit more about that later. Okay, so the things that we have to do to improve our WIMP detectors are to beat down this radioactivity and also to make larger and larger detectors. And one last thing is that at the left-hand edge here, it looks like the background is taking off. Really what that is that we have no information. Once you go to very, very low energy, we just become blind at that point. It's sort of lost in the electronic noise of the detector. So what we want to do to make better WIMP detectors is to push down the radioactivity, scale up the mass, do longer exposures, and push down the energy threshold to see even the possibility of seeing lighter and lighter WIMPs. So these are the various challenges to a WIMP hunter. Okay, so what do we have to work with? There's energy deposited in a detector, and that's basically what you have to work with. The three main ways that shows up in a particle detector are the ionization, like I mentioned already in that germanium detector. There are certain materials that scintillate or emit light. You send the atoms into some excited state, and when those atoms relax, they produce scintillation light, and in scintillators, maybe about 1% of the energy comes out in light. About 10% of the energy comes out in ionization. And then the slowest signal, but where all of the energy eventually shows up, is in heat. Turns into heating the detector. That's a hard signal to measure. And now there's a sort of a variety of approaches around the world. Some that just use one channel, like these germanium ionization detectors, or very simple scintillators that you can scale up to be very large in size. And then there are different classes of detectors which try to measure two different channels at the same time, light and ionization, like the experiments that I work with, ionization and heat, like an experiment I used to work with. And anyway, you can kind of piece these together. This is kind of the art of doing this kind of work, is finding, what does nature have to offer in terms of materials, what sort of sensors, what kind of electronics can we put together, what materials have low intrinsic radioactivity. There's all sorts of considerations that go into how you pick a given detector technology and how you push it along. So what we want in a detector is low radioactivity, immunity to backgrounds, that it can be large mass and be able to operate stably for years even, that you can shield it from external radioactivity, and that it has a low energy threshold because these WIMPs are just not moving very fast. Okay, so the technology that we've been working with is called the liquid xenon time projection chamber. This was a type of detector invented for accelerator-based particle physics, where you were, let's say, colliding an electron and a positron, and you wanted to study the pieces that came out. And the motivation for this type of detector was that whenever you were building an instrument, you have to always make it out of something. You can't make your detector out of nothing, because then it doesn't do anything. And so, but the material of the detector itself is often getting in the way from the very things that you want to measure. And so this very inventive physicist, David Nygren at Lawrence Berkeley Lab, said, well, why don't we push all of the instrumental stuff out to the edges and just fill the center with active medium. So just with whatever material, in our case, the liquid xenon, you want the radiation that you're studying to interact with. And this became a very fruitful enterprise. The idea of the time projection chamber is that you basically have a start signal and a stop signal. Now, if you're doing a beam experiment, you know when the particles were sent into your detector, and then you can measure when those particles are flying out, and you can piece together tracks. In a dark matter experiment, we don't have a beam. We don't know if the particles are even there, and so we need to combine a pair of signals in the detector on an event-by-event basis to figure out where things were. So the model that we have is that a particle comes in, it strikes a xenon atom or the electrons in a xenon atom, and it creates a small amount of this scintillation light. That scintillation light rattles through the tank and gets detected, and it's kind of a diffuse way in photomultiplier tubes at the top and at the bottom of the detector. And then some of the energy goes into, and so that's our start signal. That's when you sort of start your stopwatch. And then some of the energy goes into fully ionizing the xenon. So electrons are liberated. And we put the whole detector inside an electric field so that the electrons are drifted up. So the electrons travel up through the liquid, and eventually they reach the gas-liquid interface. And there's a stronger electric field there that pulls them out of the liquid. And that makes a second flash of light. And that's kind of the snapshot that we have here. So then the array of photomultiplier tubes at the top measures that light in a sort of like, it's almost like there are pixels, although they're very coarse pixels. There's a few hundred tubes at the top and a few hundred at the bottom. So where that light came out tells us kind of the XY coordinate of where the event took place. The electrons don't rattle around very much, so they pop out and you measure the XY coordinate. Then you also measure the time that the electrons popped out, and you compare that to the start time where you saw that initial flash of light. The velocity of the electrons is fairly well defined, so now you can work out what the depth of the event was. So now we can image where that event took place in 3 dimensions. And one of the reasons that is really important is because it's impossible to get rid of all of the radioactivity. So there are radioactive materials in the walls of the detector. You've done everything you can to screen them and make careful choices, but there's still going to be some radioactivity. That radioactivity, for the most part, stops in the first 5 or 10 centimeters. Whereas WIMPs, since they're very penetrating, most WIMPs will go right through the detector. You hope for the occasional WIMP that interacts at any random location. By knowing where the event took place, we can say, well, if it's in the outer edges of the detector, let's throw away that event. There's too high a chance that it was due to radioactivity. But then you end up with this very nicely shielded region in the center of the detector where the radioactivity, for the most part, doesn't reach. And so you can have this very clean inner region. In the jargon of our field, we call it the fiducial region. So if we have a nice big fiducial region and we throw away just the outer 15 or 20%, we can make a huge reduction from signal to background. Right? This is like the equivalent of going from doing astronomy during the day to doing astronomy at night. Okay, we get rid of a lot of background that way. So this was very fruitful. This led us to build the LUX experiment, the Large Underground Xenon Experiment. So this was about 250 kilograms of xenon that was condensed inside a double-wall titanium vessel. Inside that vessel is basically, at room temperature, an empty barrel of Teflon. Teflon turns out is a good reflector for the light that is produced in xenon scintillation. And then looking up before the bottom was put on, you can look up and see the array of photomultiplier tubes. So that whole thing is buttoned up, and it's put inside a not yet filled water tank where one of our graduate students is standing for scale. And then this whole thing is installed in the Homestake mine in Lead, South Dakota, about a mile underground. Why underground? Because there are still more backgrounds. There are backgrounds associated with cosmic rays. So standing here on the surface of the Earth, there's a continuous rain of subatomic particles from outer space. So if I stick out my hand, there's about 1 cosmic ray muon per second that goes through my hand. And you definitely don't want these particles interacting in your dark matter detector. They would completely mask a signal and even generate radioactivity. So to get away from these muons, we go mile underground, and that most of them range out, and they're just stopped by the Earth. In the water tank itself, we get additional shielding if there's radioactivity in the walls of the cavern. That can liberate neutrons or gamma rays, and all of these things are very effectively stopped by a few meters of water. So you build your experiment, you remove your students, you fill it up with water, and you run. And we ran, and we ran, and we ran. So this is what the signals in the detector look like. This is calibration data. So this is a graph of the 122 different photomultipliers in the detector. We start the clock when we see the first scintillation signal. You can see that most of it shows up in the bottom PMT. So if you've ever looked up from inside a swimming pool, you see total internal reflection. Much of the light is totally internally reflected, and so it's mostly collected in the bottom. And then for a couple hundred microseconds, almost nothing happens. There's a little bit of noise in a couple of tubes there. The electrons drift up, they hit the surface, they get pulled out, and they make a second flash of light. And that's concentrated in a handful of phototubes that gives you that XY localization, right? And then again, the time difference tells you the Z position, the depth in the detector. Now that's a nice big whopping calibration event. A WIMP event looks a little bit more like this. This isn't a WIMP event, but this is what a WIMP event might look like. We can start the clock with just 2 scintillation photons. So now we have this like macroscope, a couple hundred kilograms of material, and it's just sitting there quiet. And if we get just a couple of phototubes with a single photon in each of them, we can start the clock, and then voila, a couple hundred microseconds later, the electrons hit the surface, and we get the second signal. And so we this is the sort of data that we look for in our WIMP data. Now, when I started graduate school, one of my elders said to me, "There's a word that one day is going to make your life miserable." And I was like, "Tell me the word. I must know the word." And the word was calibration, right? So calibration is how we think we know what we know, right? So and boy, he was right. I had plans to finish graduate school, and before my postdoc, I was going to take a one-way trip around the world with a backpack and all this. Calibration calibration. In the end, I took a car trip to Maine with my sister. So it was very nice. But calibration really took a lot of time. So the way that we calibrate the LUX experiment is by actually dissolving some radioactive material inside the xenon to light it up from the inside. And this was a big challenge because we designed the experiment to be large enough so no radiation could get in from the outside, because you wanted to shield that nice inner fiducial region from the radioactivity. So now, in the old days, you would just hold up a radioactive source, light the detector up for a little while, take some calibration data. So now we had this problem where we can't get radiation to the inside. We've gotten rid of all the radioactivity, so how do we light up the detector to calibrate it? So one of our collaborators at the University of Maryland, Carter Hall, came up with a technique where he got methane gas. So this is carbon with 4 hydrogen atoms. And one of the hydrogen atoms was replaced with a radioactive isotope of hydrogen tritium. And boy, we were nervous, because here we were, we'd made this super clean experiment with no radioactivity in it. And here we were going to inject radioactivity into the detector, because then that methane, tritiated methane, would dissolve throughout the xenon and light the detector up everywhere. And we had long meetings and task forces and all of this. And we finally, we tested it with untritiated methane, and we convinced ourselves we could take the methane out, and then we just put in a little bit to see a few hundred events, and then it came out, and finally we went for it. So we dosed up the detector, and we got these amazingly beautiful calibration. I mean, to me, this is beautiful. Karen, isn't this beautiful? Yeah. So what did we do here? So what we're plotting is the ratio of the S2 signal, the charge signal, to the light signal. And we're doing that for background-like events. The tritium gives us beta decays, electron recoils, which are different from the WIMP recoils that we're looking for. And then we plot that versus the S1 signal, which is kind of roughly how much light, how much energy was deposited in the detector. And so we make this graph of this ratio versus energy for the background-like events. And then we do the same thing for signal-like events. Now, again, we don't have a beam of WIMPs, but we have the next best thing, which is a beam of neutrons. And so neutrons, like WIMPs, have no electric charge. And so when they interact in the detector, they're mainly going to scatter from a xenon nucleus. So this signal-like calibration. Neutrons are like WIMP test particles. And so we make a graph of the response of the charge to light signal for the nuclear recoils, and we can use this comparison here to tell the difference at about the 200 to 1 level, the difference between a signal event and a background-like event. So the way that we analyze this data is to say, okay, this is what our signal is going to look like. So we fit this red line, goes right down the middle of the distribution, and we plot that red line up in the other graph where we have background. And you can see that most of the background lies above this red line. So what it says is that if we only accept WIMP recoils that are below this red line, throwing away, let's say, half of our signal, we can get rid of 99.9% of the background. Okay, so this is yet another tool that we have to try to discriminate between a WIMP-like event and a background-like event, because you can never really get rid of all the radioactivity. So this calibration is wonderful because it tells us exactly what the background is going to look like throughout the region of interest, and then with the neutrons, what the signal is going to look like throughout the region of interest. And you may have noticed these little these look like kind of cigars here. This is counting individual photons that show up in the photomultiplier tubes. This is like this is like a 2-photon event and a 3-photon event and so forth. So you can count individual photons. So then we button up, we get rid of our calibration sources, and we run, this was the first run for about 100 days. And we make the same plot of the charge over light versus energy. And what do we see? We see about 100 or so events that populate this so-called electron recoil, this background-like band, and we see no events below the red line. So thanks for coming. No, there's more. So with this graph, turns out we were the best in the world at seeing nothing. Okay. So this was a world best result. We got to draw a lower curve in that cross-section plot. In fact, it's the next slide. We got to draw, so this combines actually with our subsequent runs through 2016. We got to draw this curve saying that, we've searched longer and further down this graph than anyone else. And okay, sorry, WIMPs weren't there. But, that's still progress. So undaunted, we said, well, obviously, we need a bigger detector. So this is the LUX-ZEPLIN experiment, expanding from, pick a number here. All the numbers here are bigger than all the numbers in LUX. So the 100 kilograms in the center of LUX, that nicely shielded region, will now be expanded to 5.5 tons. So that's like a factor of 50 increase, and we're pushing down backgrounds, and oh, it's going to be wonderful. Okay. So a little bit more about what the detector looks like. Mostly, it's a scaled-up version of LUX. More mass means more exposure, more chances for a WIMP to hit a nucleus. But we've added another thing. We're actually installing it in the same cavern, in the same water tank. But we've added another detector here in green, which is another type of scintillator. It's not sensitive enough to be a WIMP detector, but it's going to be a very good monitor of whatever backgrounds are still left. Things that will produce backgrounds in the xenon have a very good chance of also producing signals in the outer scintillator detector. And so it'll be kind of an ongoing monitor. And I'll have a couple of graphs in a moment to show you how well that's going to work. So we call this now, of course, LUX was a discovery instrument. We call this is a discovery instrument because it has a really good monitor of the backgrounds. That way, if we see a single nuclear recoil below the famous red line, and we don't see anything in the outer detector, or even our long-term studies of the ambient background in the experiment that we learn about from the outer detector will give us really great confidence that we understand kind of the overall environment, so that if we do see something, we'll hopefully be able to make a credible claim. So, most days I don't sit around with my feet on the desk thinking about the Big Bang and the freeze out of WIMPs and all that. Most days I'm doing sort of more practical things, and I wanted to take you through a few of the things that we're doing at SLAC to try to build the LZ experiment. So one is weaving and testing grids. So the grids are these sort of diaphanous wire meshes that are at the top and the bottom of the detector, so we can set up this electric field. The challenge with the grids is that we want them to be as transparent as possible because we're also trying to detect this very weak scintillation light signal. And so we went down to the stock room, and they didn't have any unobtainium, which is the magical material that you want to make all of your physics experiments out of. So you have to make it again out of something. And so we had to start from scratch with the world's oldest textile technology. We actually built a custom loom, and we're starting to weave these wire meshes out of just the right type of wire at just the right tension and just the right size and all that. You can't buy it in a catalog. I actually took my first shift of weaving on Tuesday evening, which was a lot of fun. I did there's the warp and the weft, and I got to do the warp wires, and maybe next week they'll let me come in and do the moving parts where I get to do the weft wire, so it's really fun. So the challenge with these grids is that we have to put them up at high voltage, and we're very sensitive to very small amounts of stray light. I showed you the LUX event had like 2 photons was enough to start the clock. So now we have these imperfect wire meshes. We're going to stick them in liquid xenon, and we're going to crank up the voltage so that we can drift electrons from the bottom of the detector to the top. Well, what if there's a tiny nick on a wire? It's going to create a little high field region, and the xenon is all set to start glowing with just a little bit of energy. And so we're making small practice grids, 20 centimeters across, testing them in liquid xenon, measuring their properties, their emission, and all that. And then we're making full-size grids. They're about 1.5 meters in diameter. And we're testing those just in xenon gas because we just don't have the time and the wherewithal to try to test full-size grids in a big 500-kilogram puddle of liquid xenon. It's just too much. So we're going to try to piece together enough evidence in our test lab at SLAC so that when we do finally make the final grids and test them in gas, we can be reasonably sure that when we build the experiment in South Dakota, button it all up, turn on the high voltage, that we'll reach our performance targets, and we won't get stray light. So here's a couple of our group members testing the small prototype. So these are about 20 centimeters across, and that will go inside of our liquid xenon test vessel. Okay, but there's more. So there's another challenge that we have, which is the xenon that we use comes from the atmosphere. That's where xenon comes from. It's about 1/10 of a part per million in the atmosphere. And when you collect the xenon, you also collect krypton, which is about 1,000 times more abundant. And the krypton has a radioactive isotope. And since it's a noble gas, so this would be just like the tritium dissolved throughout the detector, lighting it up from the inside, which we can't tolerate. That would be blue sky. It would mask our WIMP signal. And so we have to get rid of this krypton. And it's long-lived. It's got a 10-year half-life. So we can't just buy the xenon and wait. That would not be good for the graduate students. And so we need a way to take it out. And normal purifiers don't get rid of noble gases because they don't interact chemically. And so the technique we've developed uses gas charcoal chromatography. So the idea of chromatography is that you have some medium, and you have some different things, let's say ink and different sized pigments in it, and a solvent. And those pigments will move at different speeds across the filter paper. So we do the same thing with xenon and krypton that we're trying to separate inside a column of charcoal. And the equivalent of the solvent is helium gas. So the helium just moves nice and rapidly through the charcoal without sticking. And the xenon and the krypton stick a little bit, and the krypton sticks a little bit less. And so it will flow through the charcoal more rapidly. So here's like a krypton signal coming out first, and then a xenon signal coming out second. And so we're basically building a giant gas purification plant at SLAC that will process a couple hundred kilograms a day. We've got 10 tons of xenon to use for the experiment, so we're gonna put that through the system twice. And we're gonna try to push the krypton concentration. It starts at about 10 to 100 parts per billion. We're going to push it down by a factor of 10 million, down to about 15 parts per quadrillion. So for those of you who are familiar with the idea that neutrinos are coming from the sun, the so-called PP neutrinos, at this concentration, the beta decays from the krypton 85 nuclei would give us a background at about only 1/10 of the background from solar neutrinos. So when we started setting up at SLAC a few years ago to do this work, the laboratory management wanted to know what we were going to do with the waste radioactivity, because they were worried that our neighbors would somehow get scared that we were going to be an environmental problem. So I was like, no, guys, there's very little radioactivity in the original xenon. And they weren't having it. None of it could go in our media stuff about the purification stuff that we were doing. So I went and I calculated for them. The original radioactivity in 10 tons of xenon is equivalent to about 20 bananas. Okay. So someone actually took the time on Wikipedia to write the banana equivalent dose of radioactivity. We get about 100 banana equivalent doses per day, just from radon and cosmic rays and all that. You can no longer buy bananas at the SLAC cafeteria because they're radioactive. So, okay. So I said I was going to tell you a little bit more about this outer detector system that we use. There's actually two pieces to it. One is the scintillator, and the other is that there's sort of a skin of xenon outside the active region, right? So there's that nice 7 tons where we're drifting electrons and we have all the photomultiplier tubes. But there needs to be a little bit of space, about 5 centimeters between the cage that sets up the electric field, that sort of Teflon and electrical thing, and the wall of the vessel that holds all the xenon. We call that the xenon skin. So we can't search for dark matter out there. And if there are some sources of radioactivity that are coming from the inside of the detector, they might interact in the skin before they get to the scintillator as they kind of make their way out. And so we also instrument this so-called xenon skin. So this is now a graph of what the background in the detector will look like versus depth and radius squared. So as you move further out from the center of the detector. And if we didn't have the outer detector, and we could only use this fiducialization, throwing out the outer edges of the detector, then we'd only have enough cleanliness in kind of the inner 3.3 tons. So we'd only get to use about half our xenon to search for dark matter. If we add in the skin and then add in the skin and the scintillator, then our simulations tell us that we can do a lot better. We can use sort of the inner 5.5 tons to search for dark matter, in addition to having all that extra information about what's the ambient rate of neutrons, what's the ambient rate of gamma rays, and so that can really inform our models of the background, because you're always measuring your signal against how well you think you understand the backgrounds. So now we can use those same simulation tools to chart what 1,000 days of LZ data would look like inside that inner 5.5 tons. So this is that same quantity of the discrimination parameter versus the energy. And so we expect to see background events from radioactivity, and in fact, I think more than half of these are due to the solar neutrinos interacting with electrons in the detector. There's another population of neutrino events from the boron-8 neutrinos of the sun, and then these events are what a particular WIMP model would look like. Of course, they don't come with red stars in the data. We have to try to differentiate them from these other distributions as best we can. So our plan is to run this for 1,000 days, and of course we hope that we see something. But if we don't, then we'll be drawing curves like this, which extend our sensitivity beyond kind of the final results from LUX by a factor of a couple hundred. Of course, some of our competition will try to chip away at this in the meantime. But we'll see how we do. So just to summarize, I think there's still exciting years ahead for dark matter detection. These liquid xenon TPCs have been dominating the field since over 10 years now. LUX was a nice run for us. We didn't see dark matter, but we improved sensitivity by about a factor of 10 compared with previous experiments. And then, as we push down in sensitivity, we'll get closer and closer to this neutrino floor where neutrinos start to kick in and would mask a dark matter signal. So thanks for your attention.
Time for at least a few questions. Bob? How is the light produced when these electrons get accelerated upwards? Does it run into something that...
So while they're in the liquid, they're not acquiring enough kinetic energy to interact. So it's dark while they're drifting, and then once they're pulled into the gas phase, they're just colliding with xenon atoms in the gas, and it's more or less the same process. There's an electroluminescence effect. They excite a xenon atom. It forms a short-lived dimer, sort of a short-lived xenon molecule, and when that xenon molecule relaxes, just as in the liquid, it produces UV photons. Yeah, sure.
In the liquid xenon time projector, how do you ensure that the incoming particle is a dark matter particle, or can it be any type of particle?
Yeah, no, that's a good question. So the best that we can do is by going deep underground, we get rid of stuff associated with the muons. By putting it inside a tank of pure water, we can try to screen out radioactivity from, the rock of the cavern, because to first order, everything is radioactive. And then our scintillator helps a little bit. And then the outer skin helps a little bit. And then the outer xenon in the active region helps a little bit. But then there's still something that's going to get in. So we can have these sort of layers of shielding.
So the idea of blocking the regular particles, but because dark matter has high penetration.
That's right. It can always get in, right. In fact, we could even detect dark matter particles that came up through the Earth. Most dark matter particles actually haven't scattered off anything since they were produced in the Big Bang. Yeah. So we're hoping to shock a dark matter particle one day by a smack into a xenon nucleus. Yeah. What happened? That's right. Yeah. So the Earth's crust is about a part per million uranium and thorium. And so that stuff pretty much just gets everywhere. Almost any sort of random piece of material that you pick up has got too much radioactivity in it to be present anywhere near a dark matter experiment. So it's just kind of, think in terms of radioactivity is everywhere. And what we need to do is select and fabricate materials very carefully to get rid of that unwanted radioactivity. Yeah, okay. We can't. What's going to happen, I didn't say too much about this, but at some point we're going to start encountering different sources of neutrinos, which will give rise to nuclear recoils in the xenon that we won't be able to distinguish from WIMPs. So there are cosmic rays interacting in the atmosphere that produce high energy neutrinos. There's neutrinos coming from the sun. And there's even another population called the diffuse supernova neutrino background. So from all the supernova that have ever gone off, there's kind of a background gas of neutrinos. And we can't shield against any of those things. And so once we push down to maybe, like if we did another experiment after LZ of, say, 50 tons, and there are groups that are doing some studies to see if it's practical, then we would start to encounter this so-called neutrino floor. Now, because nature hasn't told us what the cross-section is, maybe nature's mean. So far, it's been kind of mean. Maybe it's really mean, and it's picked a WIMP that's here. We won't see it. We won't be able to say it's there or not. Not all questions can be answered. Yeah, it'd be sad. It's here. It's going to be here. So the LHC curves are kind of orthogonal to this particular graph. So we can ask about a particular model in supersymmetry and ask, will the LHC see it? And will that model of supersymmetry also produce detectable dark matter? And these are not the right variables. So this already, well, there are models that I could have plotted on this graph. I think they're on the kind of zoomed in version up here. These different blobs are different particle physics models that could have produced dark matter. They're still allowed by the LHC, and we haven't yet searched through them with dark matter searches. So there are some particle physics models that weren't seen at the LHC and we've ruled out. There are models that neither of us have studied yet. So I'm not sure I'm really answering your question. No. Yeah. Yeah. Not at all. Not at all. Yeah. In fact, what we hope to see is that something that we see go bump in the night shows up with similar physics in the LHC. And that would really be a way to try to put together a coherent solution to the dark matter problem. Right? So you really want both. You want to study it in the laboratory. You want to know that it's actually there in the galaxy. So machos, that refers to it was an alternative dark matter hypothesis for a while. Machos, massive astrophysical compact halo objects, I think is what, and it was obviously fun. There were the WIMPs and there were the machos. What these refer to are sort of Jupiter-like objects in the galaxy, sort of failed stars. And so sort of two things. One is that those presumably would have been made out of ordinary matter, so baryons, the stuff that we know there isn't enough of to make up cosmological dark matter. There might have been enough of that stuff to solve the galaxy rotation curve problem. And the way that they were searched for was similar to the sort of that gravitational lensing graph that I showed early on, but these weren't strong enough gravitational lens to actually produce multiple images, but just would do a little bit of lensing. So if you were looking at some background object and a sort of a Jupiter, a dark star went by, it would cause a characteristic brightening over a period of days to weeks of that background object. And this technique was actually used and discovered a population of such objects by using this microlensing technique, but they weren't enough to account for the galactic dark matter. And so, they led us to continue with our search.
One more?
Sorry, the shape of the limit curves? Yeah, sure. So kind of alluded to that when I was talking about what was going on in that early germanium detector. You in any detector, you eventually hit a point where there's just not enough visible energy to see in the detector. So for us, in the LUX experiment, that first scintillation signal, we needed a minimum of 2 scintillation photons, 2 detected photons. So that defined a threshold for our detector. So that meant as you dial down the WIMP mass, eventually you aren't depositing enough energy to be seen. The WIMPs are so light that they just don't transfer enough energy to a xenon nucleus. And so the curves tend to just turn up once you run out of energy threshold. So that's them turning up at the low side. On the high side, as you turn up the WIMP mass, you're dialing down the number density. And so you just start to lose sensitivity from that point of view. And then there's also this kind of a kinematical sweet spot, which is when the WIMP mass is matched to the mass of your detector nucleus. That's when the most favorable energy transfer takes place. And so that accounts for kind of that maximal sensitivity point.